This is Stewart Calculus, Early Transcendental, 8th edition, section 2.5, number 19. I've added on a little bit to this problem where I ask first to state the three-part definition of continuity of a function f at a number of a. This idea of a three-part definition is sort of taken from one of the pages on Stewart Calculus, and what I've sort of gone with. Some people might not really think that there's three parts, but I'm going to say that there are. That first of all, f of a is defined. That's the first thing we need for a function to be continuous at a. That is, a is in the domain of f. That's needed in order for a function to be continuous at a. The next is that the limit of f of x as x approaches a exists. That limit has to exist. And thirdly, to sum that up, to put everything together, is that the limit f of x approaches a equals f of a. Now, there's other definitions of continuity, but really many people would just say, well, okay, I agree that you could sum up all of these here in this last statement. This last statement implies that a is in the domain of f, in other words, f of a is defined, and that the limit exists, and that the limit equals the value of the function at a. Okay, but I like to break it up for teaching reasons and to learn things. Now, let's look at this particular problem, number 19, where we're supposed to sketch the graph of the function and then explain why the function is discontinuous at a equals -1. Now, this right here is a piecewise defined function, and what I am going to do with this is, let's see about this, is I am going to make a little dotted line at this cutoff point. Oh, hold on, cut it the wrong place. Okay, I'm going to make a little dotted line at this cutoff point, which is at x equals -1. That's not a vertical asymptote, so in fact, I might just want to get rid of that. But anyway, it's not a vertical asymptote, but does that hurt to have that there? Maybe. Okay, and what I want to do is I notice that the domain of this function is broken up into two parts, x less than or equal to 1 and x less than or equal to -1 and x greater than -1. Now, let's shade in the plane where x is less than or equal to -1. And see, the cutoff is that dotted line. So that's not meant to be a vertical asymptote. All right, so I'm just shading that in. Totally unnecessary. I'm doing this to explain it. We'll see if that helps explain it. But over here, I have x less than or equal to -1, and then I'm going to use the rule that y equals x plus 3. All right? So for this problem, for this function, we know that m is a line and that the slope is 1 and the intercept is 3. So I can find 3 is the intercept. Now, let me draw the whole line and then I'm gonna back up on that. But anyway, if 3 is the intercept and 1 is the slope, what does that do? That means that if I start at that intercept 3 and I go up 1 and over 1, I get another point. Up 1 and over 1, I get another point. Or I can go, okay, so up is positive, to the right is positive. So it's rise over run, up 1 over 1. Or I can go down 1, which is -1, to the left 1, which is -1. And so -1 divided by 1 makes 1 in the slope. And then I have a line that passes through those. Probably too much. That's a beginning algebra skill. But anyway, I did that. Let's make that a brighter color and a little just thicker, why not? And let's see if I can extend this line over here. Now the thing about this is hold on. I just want it really good. But maybe good, does this have to be really good, just sort of good? Okay. I put 3 here, and I have a line going all the way out of that orange region so that I can understand it, teach it better. But actually, the line only goes up to x is -1. Why? Because this is the rule that works in this, this orange region that I've drawn, which is x less than or equal to -1. And then on the other hand, when x is greater than -1, I can pick another color here and shade that in, although it's totally unnecessary to do the shading stuff. But I'm just doing it because I think it might explain it better. Okay, and it's fun because I have this iPad to do this on. Okay, so then for x greater than -1, I'm going to look at, x greater than -1, I am going to look at y equals 2 to the x. All right, and you can plot points, so that's going to sort of make a mess of what I'm doing here, but still, here's x, here's y equals 2 to the x. Let's see, I can put in -1, even though actually -1 is not in, we don't use this rule for y equals 2 to the x, but let's just try that out. We have 2 to the -1. Put 0, 2 to the 0, 1, we get 2 to the 1, 2 squared. Can we go all the way to 3? 2 to the third. 2 to the third is 8. 2 squared is 4. 2 to the 1 is 2. Let's see, if I divide 8 by 4, I get 2. 4 divided by 2 is 2. 2 divided by 2 is 1. Below that is 1/2. Let's see if I can extend that. Make that look better down there, a little bit better, maybe not. Okay, back to pink. So I can plot some points. 2 to the -1, I get 1/2, but actually I don't really want to include that, so I'm just going to put an open circle for that. Then I have 1, I'm going to plot that point. 2, 4, and 8. 5, 6, 7, 8 is way up here. So this is the exponential, 2 to the x. All right, so mostly that was a challenge or something to do where we sketch the graph. By the way, also I should not leave off that we can plot points for our line also, which works, really well. You can put in -1, -2, -3. So that's always a good one. Plot some points. And so we get -1 plus 3 is 2. -2 plus 3 is 1. -3 plus 3 is 0. And that's what we see from this, from what we have here. I mean, it's a little messy when I put all these markings on the x and y axis. So, all right. Okay, so let's go through now. Why is the function discontinuous at a equals -1? The function f is discontinuous at a equals 1 because, okay, let me talk this through hopefully that'll be all right without writing it down. Let's go through and check these off, in fact. Does f of, sorry, I wrote it down wrong over here. But now I don't think I can even fix it very well. Okay. It's discontinuous at -1 because why? Let's go through this piece by piece f of negative 1 is equal to, if I'm looking at this picture, it's 2. Got that. And the limit of f of x as x approaches negative 1 is equal to, oh, hold on, it doesn't exist. I'm going to erase the equal. Why doesn't it exist? Because the left and the right hand limits are not the same. Okay, they don't. From the left, you can write it out. I'm just going to, but we can see the limit from the left is 2. If I go along this graph, I see the limit from the left, just to make a bigger mess, is x goes from negative 1 from the left is equal to 2. If I come on the other side, I see the limit of f of x is x goes to negative 1 from the right is equal to 1. Oh, no, not even 1, 1/2. Not to say that 1/2 isn't just as good as 1, but anyway, the limit doesn't exist. Okay, the limit does not exist. So the function f is continuous because the limit of f of x, x approaches negative 1, does not exist. That's what we're supposed to do. We're supposed to sketch the graph and then explain where the function is not continuous, but actually they tell us it's not continuous at negative 1 to begin anyway, but we're supposed to explain why. And I'm saying because the limit doesn't exist, and that is part of my 3-part definition, the limit has to exist. All right, so that's a lot of stuff. I mean, I think it could be way shorter if I didn't write all these little notes, especially plotting points. I mean, a line and y equals x plus 3 and y equals 2 to x are elementary functions, so I don't really think it takes quite as much. And for plotting points, you can plot a lot of points just by, adding those numbers in your head. So, but that does it. All right, so goodbye.